Okay, so welcome everybody to this second session of the masterclass. And we will start with Xavier Buff, who will speak about geodesics on an affine surface.
Okay, thank you. So I will talk about a subject that I'm currently studying in my research work. And I will try first to give some motivation. But the subject in itself is interesting. I will have to define what is an affine surface at some point, and to define what is a geodesic on an affine surface. And before going to that, I will just start talking about sequences defined by induction. And this is the motivation for me to go into the subject. But there are other people working in the subject of geometry rather than dynamical systems, which are interested in flat surfaces, affine surfaces, dilation surfaces, and the geodesics on the surfaces and how they behave. From a geometry point of view, and I will have a dynamic point of view. So for me, a dynamical system, it's a map from a space to itself. And if you have never studied Gea sets or Mandelbrot sets or fractal sets, I should have started with going from the complex plane into itself, which is already very interesting in itself. But since I want to go to geodesics on affine surfaces, I will directly start from a map going from C2 to C2, not one complex variables. The subject of going from C to C and studying sequences defined by induction in C goes back to the 80s, 1980s, or even to the work of Fatou and Gia at the beginning of the 20th century. Going to two complex variables goes back maybe to the 90s, and making a link between this subject, iterating a map from C2 to C2, and geodesics on affine surfaces goes back maybe to 10 or 15 years ago, without anything in between, and so okay. So we start with an initial point, so you know about sequences for sure. You start with an initial point, and then you look at the sequence defined by iterating xn plus 1 is f of xn. Except here that I have two coordinates. And the question when you do dynamics is what is the long-term behavior of the sequence. So probably what you have been studying is whether the sequence converges or not. And here it could be more, so the questions would be more like, are the sequence bounded without necessarily having a limit? What is the set of accumulation values of the sequence? Things like that. And maybe I should plug in my computer for it not to turn off all the time. And so I will go to an example and so show some pictures. So we can draw the pictures with a software. You have to download your preferred software or have some students doing the software for you. So an easy example is to look at the map f of xy is x plus y squared, y plus x squared. I said easy, I should not say easy. The map things are very easy, but when we start iterating the map, so let me see if I have a software somewhere to do that. Okay, so first if I want to draw a picture, what I can do is to start with an initial point in C2 and to iterate the point and ask about the long-term behavior. For example, I ask whether the orbit remains in a disk of radius 10 or whether it goes out of the radius of radius 10. And if it goes out of the disk of radius 10, or the ball of radius 10 because I'm in C2, so one of the coordinates has a modulus bigger than 10, then I will put a color, and if it goes out this disk in one step, I will draw in yellow, in 2 steps in green, in 3 steps in blue, and so on. And because I want to draw a picture on the screen, I will start by slicing the 4-dimensional space C2 with a plane. So this is the slice x is equal to -1, y. So I start with a point with coordinates x So this point would be 0, 0. This point would correspond to the point 1 minus 1. This point would correspond to the point I minus I, and the opposite. And then I start iterating the sequence, and I ask whether the orbit is bounded or not. I can also draw the orbit to show you the behavior. So if you start close to 0, because you start with x plus y squared, y plus x squared, then the image will be close to 0. So I will put successive points in the orbit. So let's say I have here, I will put 2 points in the orbit to begin with. And what I draw, in fact, because again, I don't know whether you see the first point I choose, its image, and the next image out there. And because the successive points are in C2, I'm only drawing here the coordinate x. So I project all the picture on the coordinate x. Everything is parameterized by x, so I just draw the x coordinate. And so a priori, if I'm in the colored region, what will happen is that the x coordinate isn't bounded. And if I start close to 0, the more, when I start close to 0, it will take more time, more and more time. So here I will put 2,000 iterates. So if I start close to 0, you see, if I'm in the colored regions, then the first points are close to each other. They remain close to 0 because it's really x. Is that joke? I can draw here. You just have to rotate a little. So it's xy goes to xy plus something which is y squared, x squared is very small compared to xy when I'm close to the origin. So I just move the point a little bit each step. But moving a little bit, a little bit, a little bit, then after some time, x squared, y squared becomes much bigger than xy, and this goes out of the window. If I start here, what you can see is that there are, well, some kind of structure, the successive points. So where did I start? I don't remember. I started here, and then the successive points, you see that draw like some curve before it goes to infinity. And if I zoom close to the origin, so maybe you can see some pattern, some symmetric pattern. I can see almost a square somewhere like this. And if I look from far enough, I will see some kind of hexagons and some, so there seems to be some structure in this picture. And if I iterate here, when I start just on this line, it seems that there is this nice drawing that appears, but if I start on this other line, you see it's not the same kind of drawing. And it sounds like it's very sensitive to small perturbation. I see some drawings, some nice pictures. So here it's more like a figure 8 that is drawn, and the orbit seems to get bigger and bigger. So I want to analyze this and to say something about this picture. At the moment in my research, I'm almost unable to say anything about this picture. I can see the picture, I can make conjectures. So a conjecture, for example, is that if I choose a point at random with full measure, I expect the orbit to be unbounded. That I don't know how to prove. The set of points with bounded orbit, I expect it to have interior, empty interior. I don't know how to prove that. So there are very little things I can say about this map, and the map seems to be very easy, and there are very little things I can say about this map. The thing I can say is that I can explain why do you see these nice curves that get drawn. I can change a little bit my map, and so this is the picture where it's the same picture with different coloring. And I can change the map. So the first thing I did when I looked at this picture, you can see that every time you make a full turn, it seems that you go a little further and further and you keep the same shape on this picture. So I was trying to understand why you have this behavior. And I finally understood what this behavior, how to explain this behavior. And I changed the term of order 3 in the map, the cubic terms. I added some cubic terms in order to correct this behavior that the orbit goes away. And this is the next picture. So I found exactly how to change. And I added 2x squared y, 2xy squared as a cubic term to the map. And I keep the same nice kind of picture with this figure like, you know, three loops. And this one like a figure 8. But now, instead of going towards infinity, it sounds like the orbit is going towards the origin when you iterate. But you see still the same pattern. And so I want to explain what this pattern is. And explaining this pattern will have to do with geodesics on affine surfaces. So there are some curves that are drawn, and I want to explain the shape of those curves. Okay, in order to understand the shape of those curves, I now have to change my mind and say that instead of iterating a sequence, I will look at the solution of a differential equation. So I move from sequences to differential equations. And this is still a dynamical system. When you have a differential equation, it's that you are looking, for example, as the flow of a fluid. And you are trying to understand the flow, the evolution of this fluid as time passes. And this is now in physics rather than in mathematics. And so you rather play with continuous dynamical systems and you look at differential equations. So in order to talk about a differential equation, still on C2 because I want to analyze the previous setting, you start with a vector field on C2. At each point, you know in which direction you want to move. You don't have the map that sends a point to a new point. You just know in which direction you want to move points. So this is given by a vector field. This is a vector field of speeds. You imagine that you have a trajectory and you just think of the speed as you go through a point. A solution of the differential equation is something you write as d gamma. So the solution is parameterized by time, t. So you want that d gamma over dt evaluated at some point t is equal to the vector field, to the vector you have at the point gamma of t, which I write. So the derivative with respect to t is written as gamma dot in order to keep the derivative with respect to z with respect to the variable for something else. And the equation is gamma dot is equal to v of gamma. So this is typically a differential equation. You have a vector field and you try to solve gamma prime is equal to f of gamma. So I write it as gamma dot is v of gamma, but it's exactly the same. I don't use the same letters, but so this is a differential equation. And if you have a differential equation, you can call gamma sub z the maximal solution that passing through the point z at times t equal to 0. And this you call this the trajectory of the vector field that passes through the point z at times t is equal to 0. So and now you try to understand the long-term behavior of this trajectory. Does it converge to some point? Is it some bounded? So same kind of question, except that now you have a continuous solution instead of having points that moves from one point to the other. And usually what you learn is that in order to approximate the solution of this differential equation, what you can do is to use Euler's method. And then you learn about better methods like case 3 methods or more involved numerical methods to approximate the solution of a differential equation. But the basic one is you do Euler's method with step epsilon, which means you start at a point z and you add epsilon v of z. You move by epsilon distance in the direction that is given by your vector field. And Euler's method, what you do afterwards, you just iterate you look at the sequence defined by induction starting with z plus epsilon v of z. And at this point, new point, you do z plus epsilon v of this new point and so on. So it's really now, if you want to solve numerically your solution, you look at the sequence defined by induction. And if you look, the map I was looking at was z plus v of z, where the vector field v of z was just v of xy is y squared x squared. In fact, what happened, it's an elementary proposition you can prove, is that if you start with epsilon, which is very small, and you iterate during a time which is 1 over less of order 1 over epsilon, then the successive iterates, the sequence you define by induction, are points which are very close to the solution of your equation at times j, as long as the time j is less than 1 over epsilon. I'm not sure, I think there is I will have to correct the slide because I'm thinking of j being an integer. So I think it's as long as, so here it should be an epsilon j. So fj of x should be gamma x of epsilon j, as long as j is between 0 and 1 over epsilon. So this should really be epsilon j, because you iterate with step epsilon, you move by distance epsilon, so you add epsilon to your time each step. Okay, so iterating the map will give you points which are very close to the trajectories of the vector field. And this is why you see those curves that get drawn. It's because you are close to the origin, you iterate your map, you see in fact the trajectories of the vector field. This is what you see. And so the next step is to try to understand the trajectories of the vector field. This vector field is not an arbitrary vector field. This is a homogeneous vector field in situ, which means that if you look at the point lambda x, lambda y, the vector just gets multiplied by lambda squared. So there is a scaling factor which is not acting the same way on the xy coordinate and on the vector field, but it just gets rescaled by a factor lambda to the power something, and this is called a homogeneous vector field. A consequence of this is that if you look at a trajectory starting at a point and you rescale, then the trajectory just gets rescaled. You just pass from one trajectory to the other one just by rescaling. So it's easier to understand than if you have just an arbitrary vector field, because you have the scaling action. Okay, so now I will move. I'm not yet at geodesics on fine surfaces. I will move to a third subject in dynamical system, which is billiards. So a billiard table is just a polygonal. So it can be any. A billiard table can be any region in the plane R2, and you start with a ball and you bounce against the edges of the table. And there is a rule that the angle that you use to when you come is the same as the angle you use when you exit, the angle with respect to the tangent. In this talk, my billiard table would just be polygons. It could be disk, ellipses, it could be some convex region or not convex. In this talk, the billiard will just be a polygon. And the billiard trajectory is just you start with a line, and you look at the image of the line as it bounces against the edges of the billiard table. So you can, so this is the billiard trajectory on the regular pentagon. I don't know where it started. I found it on internet. Or you can also use the software. So the software I will use now has been implemented by Arnaud Cherita, who is a mathematician here in this institute. And so I can just, so this is an equilateral triangle. I can use this arrow to draw the trajectory. And I can put, let's say, 1000. It's difficult to see the picture. It sounds like the trajectory goes everywhere in the triangle, so we would say that it's a dense trajectory in the triangle. Or you could start with specific angles when you send the ball, because we are in the equilateral triangle, doing 60 degrees to start should give something special. And indeed, if you start with 60 degrees, then the trajectory will just be periodic. So one question you could ask in terms of the long-term behavior of the sequence is it dense or is it periodic? So this is a question you can ask. Can I find other periodic directions? So if I move my point here, I keep periodic trajectories, and I have a particular one here, which is of period, I would say 3 because it bounces 3 times, period 6. Can I find different angles? So if I start with angle 90 degrees now, with angle 90 degrees, then it goes to this edge, it comes with 90 degrees and it comes back. This is because of the specific shape of this billiard table. And I could ask, so are there other, so it's not difficult to prove when you start with the equilateral triangle. What you can do is to analyze the trajectory. You could reflect along the sides of the triangle, and as you reflect along the sides, then it's as if you were continuing straight, in a straight direction, but you reflect, and then you reflect among the sides. And because when you reflect the equilateral triangle in the plane, you get a tiling of the plane, it will be very easy to analyze the behavior of trajectories in the equilateral triangle. And the result you can prove, I think it's on the next slide, I'm not sure. No, it's not on the next slide, but I will state it now. If you look at the slope, not the angle, but the slope of the trajectory with respect of the bases given by the 2 edges here of the triangle, and you look at the slope, if the slope is rational, the trajectory is periodic. If the slope is irrational, then the trajectory is dense. And this is obtained just by analyzing a rotation in a circle. If the angle of rotation is rational, counted in turns, the orbit is periodic. If the angle is irrational, then the orbit is dense. So in the case of the equilateral triangle, you can analyze all the behavior of orbits. Now what is very interesting for me is that if I go back to my subject, there is a theorem 2009 of somebody called Ferran Valdez, who was doing his PhD at Rennes at that time, who proved that understanding the trajectory of the differential equation that we were discussing, y squared x squared, amounts exactly to understanding the trajectories in an equilateral triangle. And what I've been trying to show is, you remember the trajectories we had that were doing 3 loops like this, or the next one will be figure 8 on the next slide, just corresponds to the setting where you have a triangular billiard and you go like, you bounce the first time, so the bounce, every time you bounce, you have to switch from one side to the other one in this picture, because I wanted to try to explain that, in fact, there is an inside. This is the unit disk in the complex plane. This is the complement of the unit disk. And for the vector field, the trajectory will go, if I just look, so here I'm not looking at the first coordinate x, I'm just looking at the ratio of the 2 coordinates, the slopes. And it makes sense to talk about the slope because the vector field is homogeneous, so we look at how it acts just on directions passing through the origin instead of looking at the x coordinate. And this is how the direction evolves as you flow along your, your vector field. And you see this figure with 3 loops, which corresponds to here going, bouncing again like this, that I showed you when you start with 60 degrees. And if I take the triangle and the reflection, I reflect the triangle, I get this. And this is like doing the map z goes 1 over z bar in the complex plane to understand the correspondence. And passing from the triangle to the disk here, it's just what is called a conformal representation. It's a biolomorphism from the triangle to, so we understand really how to pass from the equilateral triangle to this picture. And so this is a picture when you start at 90 degrees and you were bouncing like this. This is exactly what corresponds to this figure 8 picture that we have been drawing earlier for when we iterate x plus y squared, y plus x squared. And so there is really a correspondence, and you can do a more difficult orbit like this one, which wants to be closer to dance in the circle, and you can look for the vector field. You have a corresponding orbit that you can draw, and they really match. So there is a way you can match the orbit of the vector field with the orbit in the triangular billiard. The reason why we are working with the triangular billiard is because we chose this quadratic part as being y squared, x squared. But then the question is, okay, if I choose something else, and I chose on purpose y squared, x squared, because I knew that it would correspond to the equilateral triangle, that I should be able to understand a priori very well. And as I told you, it's not because I understand the triangle very well that I can say something about the map that I iterate as x plus x, y squared, y plus x squared. I can explain that I understand the shape, those figure 8, those 3 loops figure, but I'm not able to answer the simple question, can I prove that almost every orbit is unbounded? That I cannot prove yet. For the vector field, it's easy. Almost every orbit will be unbounded. That I can prove for the vector field because I really have a correspondence between the vector field and the equilateral triangle. But when I go to discrete dynamics, there is a small deviation for the vector field each time. And maybe you noticed when I was using the software that looking at the behavior of the orbit is very sensitive to small perturbation. Finding the rational slope, if you take a slope at random, the slope is irrational. Choose the slope at random, then you have an irrational number, and the orbit is dense. And so more difficult to analyze. But, okay, there is something worse you can do, is change your map here. Instead of y squared, x squared, just put y squared plus x squared. Just change the map. And somehow this should correspond to just change the billiard table. You start with a triangle and just change a little the billiard table and try to analyze. So maybe I will put a little less bouncing. Try to analyze, try to understand all the billiard tables. Already there are questions about billiard tables for triangular billiard tables. So I told you for equilateral triangles we understand everything. But this is not true if we are not in an equilateral triangle. This, to simplify, it's not completely exact, but what Ferran-Valdez proved, so this is correct. What Ferran-Valdez proved is that for any triangular billiard, you can associate a homogeneous vector field which will correspond exactly, the trajectories of the vector field will correspond exactly to the trajectories of the triangular billiards. So this is the statement in this PhD in 2009 is to say there is a correspondence between, there is a map going from triangular billiards into homogeneous vector field of degree 2 in C2. What do you reach in this? So this is why I want to simplify. You should imagine that what you reach is essentially vector field with real positive coefficients. Essentially, this is what you get. Vector field with real coefficients. And so the next thing is what happens if I want to look at vector field with complex coefficient, not only real, but I want to change my coefficient to have some imaginary parts. And this you won't be able to analyze using billiards. And this is where you will have to go one step further to affine surfaces. So now I will try to explain what is an affine surface. I will just restrict to particular cases of affine surfaces and to look at geodesics in affine surfaces. Okay, so this is my next step. So again we start with a polygon in R2, but now instead of reflecting along the side, what we'll say is that we'll just glue the sides. So here in this picture I just decided to glue the left side of this polygon to the right side of the polygon using the translation. So if you imagine that this is 0 and this is 1, so here is again an equilateral triangle. You glue the left side to the right side using translation by 1. You glue the bottom to the top using translation by, so this is 1 plus a cube root of unity. And if you glue the left side to the right, the bottom to the top, what you get is what is called the torus. And now when you want to talk about a geodesic, you go with a straight line, but as you come here, you just translate back by 1, and you continue. Here you translate back to the bottom, you continue. There you translate back to the left, you continue. And then so this is the orbit that is associated to this picture. And this is a periodic orbit, and this is how you can analyze, in fact, the trajectories in an equilateral triangle. It's not difficult from this to understand that this orbit is periodic if and only if the slope is rational, and it's dense if and only if the slope is irrational. And so using this translation surface, so this is called a translation surface because I took a polygon and I glued the sides with the translations. So if you do that, you get what is called a translation surface, or flat, it's also called a flat surface. And people working on polygonal billiards, they show that studying the dynamics in a billiard amounts to studying the geodesics, the straight lines, in a flat surface, in a translation surface. Now I told you that I want to change my real coefficients to complex coefficients to understand things. And this means that I will change the shape of so if I want to glue the sides with translations, I need the opposite sides to be parallel. So now what if the polygon is not so regular as a parallelogram, and it's just a quadrilateral? So what I can use to glue this side to the opposite side is just an affine map. Z goes to lambda z plus mu. Lambda and mu will be complex numbers. The translations were just z goes to z plus some mu, and the coefficient in front of lambda was 1. So what now I want to, and 1, well, was 1. So now what I want to allow is instead you take the 2 points. There is a unique affine map in the complex plane. So if I imagine that this is the complex plane, there is a unique affine map that sends those 2 points to those 2 points. And so I want to glue this side to the opposite side using this affine map. And there is a unique affine map sending the top to the bottom. And this is how I glue the sides. Which means now that when I start with a line, I come to this point, which is identified to this point. But then because this side is not parallel to this, then the direction I'm using is not parallel to the first one. There is a small rotation. And again, when I come to this point, it's identified to this point, this to this, maybe this to, I don't know exactly, so probably this. So I could play with the the software to see exactly which point corresponds to which. So starting here, this point corresponds to this corresponds to that, this corresponds to this one, and this one corresponds to that one. And I stopped and I could continue. And so now we want to understand the long-term behavior of those geodesics. So those are geodesics in affine surfaces. And so the statement is, if I want to look an arbitrary homogeneous vector field in C2, I have to understand it's exactly amounts to understanding the long-term behavior of geodesics in affine surfaces. Okay? So what kind of, and so this is a result of Abate-Tovena, which was independently to prove by Giulio Rebello, who is a mathematician here in charge of the program, is it MINT, I think, yes. So he's the one in charge of MINT, and he proved also this result independently, so that if you look at the trajectories of a homogeneous vector field on C2, and you look at the slope, the corresponding slope, and so you project to CP1, it just means that you keep in mind, instead of looking at just the first coordinate, you look at the ratio of the two coordinates y over x. So this is a complex number. And you look at the shape as you go along the trajectory of the vector field, the shape of this slope. It draws the curves in the complex plane. And this will correspond exactly to the geodesics of some affine surface. So you could just analyze it by saying I take a polygon, I glue the sides, and I try to understand the behavior of the geodesic. And it sounds like it's easier to analyze what happens for straight line as you glue with those affine maps, that we should be able to understand the long-term behavior as we did for the equilateral triangle by saying if I understand the slope, rational or irrational, then it's periodic or dense. It's not completely true, and there is still lots of questions that arise about the long-term behavior of those geodesics. So the question, for example, so what do geodesics in an affine surface look like? There are examples of geodesics which are periodic, examples of geodesics that are dense. There are even examples of geodesics which are dense in something, not the whole surface, but just a part of it. So for example, if I go, so equilateral billiards in equilateral triangles are a particular case of a fine surface. Just when you glue, they can be analyzed by when you glue with translations instead of gluing with just arbitrary affine maps. So as I said, so this I already mentioned, in an equilateral triangle, the trajectories are either periodic or dense. If you go to an open, completely open question, well, there has been work on it. In a triangular billiard, does there always exist a periodic trajectory? The answer is not known. There is a price for it, which is not much. I don't remember, it's Katok who said that for the person who served maybe $1,000 or something like that. Not much, but so there is a price, but it's a very well-known conjecture for people working on billiards. Can you prove that, try to prove that in every triangular billiard, there exists at least one periodic trajectory? So there are some partial answers. One that goes back to Fagnano a long time ago. If you try to draw a triangle within this one, and you try to minimize its perimeter, there is a very particular place where you minimize the perimeter. If your triangle is an acute triangle, then the minimum is achieved when you take the points which correspond to the perpendicular So I don't know how it's called, la hauteur in French, but in English I don't know. So you just start with an edge, you draw the perpendicular to the opposite edge, and you get 3 points. If you join those 3 points, this gives you a periodic trajectory for the billiard table. If you start parallel to it, this gives you, so in every acute triangle there is a periodic trajectory which is called the Fagnano orbit. As soon as your triangle starts having an angle which is bigger than pi/2, then this proof does not work and you have to find another periodic orbit. So there is current work, I think by, I don't remember the name of the author, that tells you with computer assisted proof that up to some angle, definite angle, there is always a periodic trajectory, but it does not cover all possible angles. A much more difficult result is that if all the angles of the triangle are rational, counting in turn, so we find again rational numbers, so you count your angles in turns. 1 turn for a full turn, and 1/6 of a turn for an equilateral triangle, and the sum of angles is 1/2 of a turn. So if you count your angles in turns, when all the angles are rational numbers, then there exists a periodic trajectory. And then you can try to count how many trajectories do you have having n bounces. And trying to count the number of trajectories, how it grows asymptotically with n which goes to infinity, is part of the work of Mariam Mirzakhani, for which she got a Fields Medal. So trying to study geodesics in a polygon is already a very difficult problem, and to count the number of periodic orbits, for example. Okay, so this is an open question. Now, I was very surprised. So last time I gave a similar talk, last year, and I did write in my slides that in a triangular billiard, the trajectories are always periodic or dense. And one colleague of mine, Pascal Rush, who is giving a class this year on the subject of billiards, she asked me, how do you prove this result? And then I don't remember why I wrote that on my slides. And I went to internet and trying to find the proof on internet, thinking that people must know about this result. And I found an article written or published on arXiv on the 30th of October 2023, so which is 1 month ago, which gives an example proving that there exists triangular billiards where geodesics are neither periodic nor dense. So this is an example of a triangle which is an isosceles triangle. The two angles here are the same. The two sides here have the same size. And I think this symmetry is important to be able to build the example. And the orbit here is dense in a subsurface but avoids neighborhood of this corner. And so there exists billiards, triangular billiards, where orbits are neither dense nor periodic. This kind of situation was already known if you don't restrict to triangular billiard, but you're allowed to work with a billiard where the billiard table has the shape of an L. And it was already known that this phenomenon where you have an orbit which is neither dense nor periodic exists. It's the fact that you try to find them on a triangle which took more time. There is a good reason why I'm interested in trajectories in triangles. It's because if I start with a vector field and I try to see how I can analyze, then essentially I will have to find an example in a triangle. The L-shaped billiard table does not correspond to a vector field dynamics. So I really wanted to see something on triangles. But as I told you, billiard table is just a sub-part of what corresponds to vector fields, because I have to work with affine surfaces where I don't glue only with translations. So first let me show how I so what is that? Oh yes, I had an animation done by Arnaud Chérita to explain about affine surfaces. I should have done that. It's this animation where you have this person that goes to the right but then reappears on the left because right is identified to the left. But you can also go to the top and come back from the bottom. And so this is moving in the torus because you glue the top side with the right side. Okay? So this is something you have to imagine that when you go straight with your geodesics, this is what you do. You just go straight and you go from one point to, and you repeat that very often. Okay, so what happens now if I move those corners in order to have, they no longer have the same size? Okay, so let's look at how my person, what happens to this person. So you see when it comes back, it gets smaller and smaller and smaller. But of course I can go the other way to get it bigger and bigger. Okay, when I go to the right, see what happens if I just go to the right, then there is this rotation effect. And each time I go through the right side, then the person rotates. Okay, and if I go, so since the right and the left have approximately the same size, if I just go to the right, the only effect is that it rotates. And if I go top or bottom, then the effect is that it goes bigger. Okay? Okay, so now I wanted to go back to the geodesics. So this again is my equilateral triangle. And what I've done is a reflection along this side. So this is the top and bottom. But when I reflect, this side corresponds to this side. So I should glue those two sides with a rotation of angle 1/3 of a turn. And similarly, this side, if I reflect, corresponds to this other side, and I should glue the two sides. And now I can just do my trajectories, which again are done. And again, if I start with 60 degrees, I will have my periodic trajectory. When I come here, it appears there and comes back, and I see the trajectory with 3 loops. But now that I'm in this situation, I can perturb my triangle to go to an affine surface. I can move this point. And I can try to analyze the geodesics. So let's start with a few, just a little less points. See, and well, there was something here that seems to happen. So I want to, so I don't know if I will be able to, so I can try to understand what are the possible. So at the moment I still have, I won't at random find the phenomenon I want to show you. I will have to compute. Okay, so let's, maybe this is not that bad. So let's put more. I'm not sure it will work. No, it's not. Okay, I won't have it at random, so I will just, okay, so what is this picture? This picture now is starting with this triangle where the orbit is dense in the subsurface but avoids a neighborhood of the corner. And here, again, I want to change. So let me try to change and see if I, let's keep the y coordinate 0 and see if I can show you, or if I don't, if if I am unable to show you the behavior I want to prove to observe, I will just have to do it not randomly, but using the exact position. Well, it's not that bad. Maybe. So let's see. No, I won't have it just being lucky. So I will have to go through the software and to put the correct angles and points. So let me see, where is my software? It's here. So I will just replace this by this. Yeah. Okay, this should work. And oops, what did I do wrong? Is that the one? Too bad. So this is not what I was supposed to do. Yes, so why is it? I have to change the script. And instead of having k is equal to 1, which corresponds to the translation surface, I have to introduce a small contracting factor to change the size. I hope this will be correct this time. Okay, so this is the kind of picture I obtain. So you see that with 50,000 bouncing, then what happened is that when you allow the side now not to be parallel and to glue with things, so the two sides on the left, if I'm correct, I'm not sure, but are glued with a rotation, and the two sides of the right there is a scaling map with factor. I introduced the scaling factor 0.8. So this is a perturbation of the previous triangle where we had an orbit which was neither dense nor periodic. Now, the first observation is that the situation is more stable. More stable in the sense that if I change the direction, not too fast, but of the arrow, you see this, I would say that this is a periodic trajectory. You just have few lines, 1, 2, 3, 4, 5, 6, 7. And in fact, they are parallel. 7 also in the other direction, and maybe 2 in this direction. And all these form a periodic trajectory. We can try to see maybe, so let's see what the period is. 14, maybe 16 or 17. So with 16, it's not closed yet. It finished there. Let's put one more. And you see 17, it passes through the point again. And if I change slightly the direction, then I keep a periodic trajectory. But if I go in the other direction, what happens is that at some point, you will lose this periodic behavior. Okay, so this is periodic with a smaller period, in fact. Ooh, it seems to be, well, let me put again lots of points. Okay, so here what happens is that if I change the period. You see, it's, I should be careful. So let me start again. I should not change too fast. So this is my, I change the direction of the ball. So for some direction it's periodic, and as I rotate, you see a discontinuity in the period. You see that you can add more points. And so what if I'm right at the correct position, so this is the initial position that I have here. If I'm right at the initial position, what happens is that when you cut transversely, you don't have just a finite number of points, but you have a contour set of directions. So essentially what you obtain, and I will stop there, is that if I were to cut here transversely, what I would obtain is infinitely many points which form what is called a contour set. You know the contour set where you take the interval 0, 1 and you retrieve the middle part and then the middle part of everything that remain and the middle part and so on. As the intersection of what remains is just a compact set with empty interior but no isolated points. So this is the definition of a contour set. And so here if I just write the direction, so for a random direction it will be a periodic trajectory, but in between each periodic trajectory there are places where the direction gives something which transversely gets contour. And so it's not, so for translation surfaces where you glue with translation, this phenomenon cannot occur. It's either periodic or dense in some subsurface of the triangle. If I allow the scaling maps, the scaling factor has an effect that when you go along, then maybe you get a little closer. Two parallel lines will be mapped to two parallel lines which are slightly closer to each other, and you can have this contour set phenomenon transversely. And so this is in my research. So this is the point where I am, where I can prove that in some affine surfaces there exists this contour phenomenon. Now what I don't know is how to deduce results from this contour phenomenon going back to the vector field or going back to the discrete dynamics, where I can really form a map with a formula for iterating a map x, y plus some homogeneous polynomial of degree 2. And I have not drawn yet what pictures I get when I iterate the map, and if this contour phenomenon has interesting consequences for the study of sequence defined by induction. So currently I'm going back and forth between those affine surfaces and their geodesics, iterating sequences, trying to understand a phenomenon. Here a question I asked to my colleagues working on the subject in Bordeaux or in Marseille. If I take a geodesic like this, whose orbit or trajectory avoids the neighborhood of the corners. Assume that it avoids the neighborhood of the corners. This is not the case. Here you see you pass very close to this point. Will it necessarily be periodic? So we strongly feel like if you say that you avoid the neighborhood of the corner, then the geodesic is automatically periodic or converges towards a periodic geodesic. So I think I had one slightly earlier there when I moving things. I told you I have a periodic phenomenon like this. This sounds like a periodic phenomenon. You avoid a neighborhood of this corner, this corner, this corner, and this corner. Just because you have finitely many lines, you avoid the corners. So if you know that you avoid the corner, and of course you can just change a little bit like this. See, if I start, then this trajectory is not periodic, but it's attracted towards the periodic one. If I start iterating, then I come closer and closer to the periodic one. So it sounds like the only way you can avoid the neighborhood of the corner is if you are attracted by a periodic orbit. We don't know how to prove this result. We think that we'll know how to prove this result probably within 1 month, but this is the kind of questions we are interested in. Okay, I will stop. It's 3 o'clock.
triangle, do we allow the ball to hit sometimes the corner? It's not a problem?
Okay, so you choose the rules. If you are doing mathematics, you have the advantage of choosing the rules. So you can decide to say that if I hit the corner, I stop. This is the first choice you can make. And ask how many orbits do I have which avoid the corner, or what is the structure of orbits hitting the corner. Another way, another rule you can choose is to say that if you are a physicist and you go close to the corner in some direction, you know that hitting the corner on the corner, you will go to some direction and you try to pass to the limit to define an extension of the map if you hit the corner and try to say, okay, what can I say in this situation? So you really choose, but of course, hitting the corner, you have to specify the rule. And you could choose, if I hit the corner, then I will start again in this one. This would not be a reasonable rule, but you are allowed to study this situation. Some people like to study the orbit of billiard table where you are outside the table, and when you hit, you come on some different side, and you just think. So the rule you decide to choose are your own rule. I guess that if you are doing research, what you usually want is to discuss with colleagues. So when you choose a rule, it has better be a rule that it will interest people, that people will say, oh yes, this is a good rule to study, I will do the same. Because otherwise you risk that you are the only one studying the problem. It's not, well, it's nice to give talks and to talk with colleagues. So usually you don't choose random rules, and you choose rules where people will think they are interesting rules. And this is not a mathematical statement. It's a human statement. You have colleagues who you believe they will like it, so it depends on the way you will convince them that it's an interesting problem. It's really a community of mathematicians.
Other question?
At many points of the presentation, you said that maybe I'm giving for parallelogram, but you said that if you have a rational slope, in some condition, you will have a periodic trajectory. But the rationality that you're talking about, is it the rationality linked with the length of the side of the
okay.
Like a triangle? Or?
There were two statements. The one you are not talking about, which was if you are in a triangle, you look at the angles that are rational, then you understand something about the trajectories. And the other one was in the particular case of an equilateral triangle, I can say something, and the reason why we can say something is that the equilateral triangle tiles the plane. You could also think of a rectangle and reflect the rectangle. You will see that it also tiles the plane. You could take an hexagon with the hexagon reflecting alongside. You can also tile the plane. So there are very few polygons where you can tile the plane. When you can tile the plane, you can analyze the trajectories completely in terms of the slopes being rational or not. So this is your question. Now the slope you have to choose is always with respect to a basis, because you remember you do the y coordinate divided by the x coordinate, so somehow you have to choose your basis. It's not a question of a scalar inner product, because it's really a question of basis, and you write your vector and you write its coordinate and you make the ratio of the coordinates. And so it's always here, the statement I made was choosing as a basis two sides of the polygon. So it's really related to the slope being rational, related to the sides of the polygon. It's not really the length, but really I choose each vector. But since we are in this very particular situation where we can tile the plane, we could say the equilateral triangle, it's the same size. But if you start talking about the rectangle, in the rectangle, then you can do the same thing and ask whether a trajectory in a rectangle will be periodic or not. So you will choose the two sides of the rectangle as a basis. And if the slope of the line with respect to the two sides is rational, then the trajectory will be periodic. And even if the ratio of the two sides is irrational or whatever it is. It's really you choose those two sides. It's not an orthonormal basis, but you don't care. You can compute the slope with respect to this basis. And if the slope is rational, then the trajectory is periodic. If the slope is irrational, then the trajectory is dense.
When you said that you can identify the sides of a polygon and use that to go from a billiard trajectory to a geodesic, is it true that like if the billiard trajectory is dense, then if the geodesic is dense, then its billiard trajectory is dense, and what if it's periodic? What information can we get by looking at the geodesic? What information about the billiard trajectory can we get by looking at the geodesic?
Okay, so let me see if I understand the question. Maybe it was this one. No, so okay. I no longer have it here. Okay, so if I want to analyze the trajectory in a, let's say, a triangle, then I can start reflecting the triangle. If I want to be able to build, once I reflect, I get a polygon with more sides. For example, I started with a triangle and I reflected it once and I had a quadrilateral. Now, if I want to glue the opposite sides, when I have a triangle, I will glue with a rotation. Okay? It's not a translation. The problem is that, so it's true in that setting that once I have reflected and I form the surface, if in the reflection the orbit is dense, then in the billiard it is dense. Because really the orbit in the quadrilateral, I just recover the other orbit by taking the quotient by the reflection, identifying the 2 points. So if I have a dense orbit downstairs, I will get a dense orbit in the billiard. Now, if my orbit is dense in the triangle, is it automatically dense in the other one? As long as I just reflected once, I would say yes. Because I necessarily have to reflect, I necessarily have to go to the other side. And my feeling would be yes, I would not be 100% sure. If I do more reflections, then it's not clear at all that it corresponds, because I could just be in a subpart, dense in a subpart of the polygon with more reflections, which would automatically, which would give density in the triangle without being dense if I take 10 copies of the triangle. I don't know if it makes sense, but you have to be careful. And a difficulty is that in order to be able to conclude, usually people don't like this rotation phenomenon and just want to work with translations. If you want to work with translation, then when you make the reflection, at some point you must have parallel sides. And this is where having a rational angle matters a lot. Because if you have 1/3 of a turn, after 3 reflections, you will get a full turn and the side will become parallel. If you have P over Q, maybe you have to do Q reflections or 2Q reflections, and you will pass 2 times or P times around this point, and you can still conclude. But this is really for building a surface with gluing with parallel sides that you use the rationality of the angles. This is why people are able to conclude when the angle of the triangles are rational, but not in general. It's because they need those parallel sides to glue things, to build a translation surface. And when you go to a fine surface where you have this change of scale, then it's much more difficult to analyze. And so the question you ask, do you have equivalence of density n1 and density in the surface? For me, it's not clear. I will not risk any bet on it. It's reasonable, but there is an implication which is clear, and the other way it's not clear.
I have a question. I will ask in French, but because I don't know how to translate it in English. Mais du coup, ça signifie que n'importe quel pavage qui change un plan, si on prend une pente rationnelle, on peut avoir du coup, on peut avoir, comment vous dites ça, mais du coup en gros on peut avoir notre répétition, oui voilà, notre périodicité sur notre pavage du coup, mais est-ce qu'il n'y a pas d'autres formes qui sont plus intéressantes qui elles aussi du coup respectent cette règle? Pourquoi du coup forcément le triangle? Est-ce que c'est le meilleur
Pourquoi des triangles plutôt qu'autre chose?
Oui voilà, c'est ça.
So, what I did not mention is that when you glue the sides here, so there is no reason why we should do triangles only. When you glue the sides here, you get a surface, and this surface has something which is called topology. This surface could be, what you obtain could be homomorphic to a sphere, it could be homomorphic to a torus, or it could be homomorphic to a surface of genus 2 that I would draw like this, with several holes, like a donut with several holes. Okay. If I want a connection with vector fields, I need to be on a sphere. And if I choose triangles, I know that gluing the two sides, this side to this side, this side to this side, it's like an envelope where you glue the sides together, you get something which is homomorphic to a sphere. The example of the billiard L gives a surface of genus 2. So so the only reason why I restrict to triangles is that if I want to go back to vector field, I need to be on a sphere. Now, people working on billiards, people working on translation surfaces, they don't restrict to this kind of things. They don't even restrict to polygons which tile the plane. And for example, I showed you a picture of a pentagon. So this is, I think, extracted from an article of Macmillan, who also had a Fields Medal, who was the thesis advisor of Mariam Mirzakhani. And with the regular pentagon, you cannot tile the plane. And here, you cannot say, so it's feasible to say that there are periodic trajectories. There is no known criterion to say which trajectory are periodic or not. You cannot say there is no slope criterion telling you if you start with this angle or parallel to this side. So if you start parallel to a side, the orbit will be periodic. So it's possible to give examples of periodic trajectories, but here, because it does not tile the plane, even if the angles are rational counted in terms, there is no algorithm, not even one you can program on a computer that tells you whether a trajectory is periodic or not. If you are on the, or maybe the article was about there is one on the pentagon, the article of Macmillan, so he gave an algorithm for the pentagon, and for the heptagon with 7 edges, there is no algorithm. So maybe it's, this is the result. And so people are trying to be able, and this has everything to do with number theory. And well, so it's a different subject. It's a link between many subjects in many areas of mathematics. So he is interested in regular polygons, Macmillan. But you can be interested in quadrilaterals, pentagon, other things. Then you choose, you study, and you see if you have a result that interests other mathematicians, and you will be able to discuss with them. And it also depends on the tools you are using to solve your problem. Sometimes the tools you are using are very elementary and you are very proud to using elementary tools, and then you talk to your colleagues and your colleagues say, oh no, too easy, not interesting. and you spend 1 month before you were able to find the very elementary tool, and you are no, but yes, once you have the solution, it's elementary, but to find it, it was not so elementary. So then it's really a discussion between colleagues. But there are lots of open problems, lots of shapes you can look at. And
another question?
Yes. You said that we have results about the periodicity or not of the trajectory of geodesics if we can tile the plane with the shape. But what if we could tile something other than the plane, such as an hyperbolic space or...
Okay, so given the rules here that you are looking straight lines, reflecting with equal angle before and afterwards, the point, what you are using is really reflection along the edge to tile. It's not only a shape you can tile the plane with, it's you tile when you reflect along the side. Because there is, for example, this weird shape that appeared this year, that a piece you can tile the plane but not periodically. So this you won't be able to analyze the trajectories because it does not tile periodically. And it's not only you just use some way of tiling. If you go to hyperbolic plane to tile, then what will be natural is to look at geodesic within the hyperbolic plane, not straight line, Euclidean line, because you are using a different geometry, hyperbolic geometry, and people are also studying geodesic in the hyperbolic plane and tiling, meaning you have the action of a group on the hyperbolic plane or the hyperboloid, and you try to count the number of periodic geodesic and so on. This is also in the work of Mariam Mirzakhani. You don't do only flat metric, Euclidean metric, but you can play with other metrics. It's called Teichmüller flow, it's called geodesic flow, and hyperbolic space. And this is what people doing hyperbolic, this is part of hyperbolic geometry, rather than part of dynamics, but it is interesting.
Other questions? If not, we can thank Xavier again. There should be a coffee break waiting for us in the lobby. You can use